Ready, everyone? Okay, now the second part of the question, the work example 2. So we are going into a different type of applications into torsions. So now, in this question, we need to apply, first before I start, I would like to remind you, we have to apply one principle of superposition in order to solve questions that is in this form, or and also we have to use your right hand rule. Okay, either your left hand rule or right hand rule by converting the torque, the turning, or the turning moment or the torque here into a straight line direction, a straight line component instead of a rotating component. So I'll teach you how to do it. Now the torque shown are exerted on pulleys A, B, and C. So you have A, B, and C. Knowing that both shafts are solid, so actually you have shaft AB and shaft BC. Okay, and I have labeled it with different color. Okay, so knowing that both shafts are solid and the diameters are AB is 130 mm, so the diameter of this is 130 millimeter, and BC, this section here, is 180 millimeter respectively. Then find the maximum shear stress in each section. It means section AB, how much is the shear stress, and section BC, how much is the shear stress. So now based on the diagram that is given, so I have redrawn it into a 2D diagram. So which shows you the pulley A, pulley B, and pulley C. But then, and at the same time, we have converted the 3.6, 10.4, and 6.8 turning moment to a linear direction component. So 3.6, and using this is your right hand rule, okay, with the thumb pointing towards the shaft axis and the fingers grips on the direction of rotation of the particular shaft or pulley. So when you apply this right hand rule onto pulley A, you will get 3.6 Newton meter acting in this direction. And then at the same time, when you use this again for pulley B, you will have this direction 10.4. And then same thing applies here for C. Then you have this component here as 6.8 Newton meter. So as you can see, this diagram here now looks like something that we have done earlier in your chapter 1, where we apply the principle of superposition. So what you need to do is, first thing is you have to check whether the total torque that is acting towards the left is equal to the total torque that is acting towards the right. So you have 3.6, and this part here should be 6.8. So 3.6 with 6.8, you have 10.4 total torque acting towards the left. So, and that is equal to the 10.4 Newton meter that is on B acting towards the right. So it is safe to proceed with the calculation work. So what you have to do is you have to split the section into, let's say for example here, 2 sections, equilibrium sections. So when I say equilibrium, that means if you see this is 3.6. So let's say we consider endpoint A first, NA, or at section A here. If we consider this as 3.6, now for equilibrium or for the state of balance, this also must be 3.6, and the arrow must be pointing in the opposite direction. So 3.6 and 3.6. So section AB is in a state of balance or equilibrium. Okay. Then after that, when you look at section B again, so I have put here as 3.6 because of this 3.6 that we have put in earlier. This is automatically, we must put 3.6 in order to balance this so that this section is also equilibrium. So 3.6, and then originally is only 10.4 in the direction towards the right. So this 3.6 of section B means we still need to add in another 6.8 in the same direction so that we can add it together to get 10.4. Okay, so this 6.8, so this must be also 6.8. So as you can see, both are opposite in direction, but equal magnitude. So that means section B, AB and section BC now is equilibrium, in a state of equilibrium. Then only you start to remember you have to apply principle of superposition and the right hand rule for any questions that is dealing with turning moment that is given in this form. Okay, you have to apply both of this theory here. Okay, so now you refer to shaft AB. So before we can calculate the shear stress of each section, you have to decide whether you are going to apply strength relationship or the stiffness relationship. So here, when you look at the question does not give us any angle of twist or even ask us to find angle of twist, neither the length nor the shear modulus G. So you don't use stiffness relationship here, only use strength relationship. So first thing, the top section AB, okay, 3.6. Then you find the polar moment of inertia, the second moment of area for section AB. So both the sections are solid shaft. That means this and this are solid shaft. So that is why we use pi d4 over 32. Unless it's hollow, then you use pi d4 minus d4 over 32. So section AB, solid shaft, diameter is, the diameter, not the radius here. The diameter is 130. So it's 0.13 to the power of 4 over 32. So you got the JAB, okay, for section AB. Then the same thing you do for section BC. The top here, BC is 6.8. So remember, don't use the wrong value for the sections that you consider. So this is 6.8, so that is 6.8. So actually they are in opposite direction. Actually, if we were to calculate the angle of twist, this might give you a positive angle of twist, and this section will give you a negative angle of twist. Because as you see, okay, this is pulling. That means when you refer to top, that means it's turning in clockwise, okay, direction, and this might be in anti-clockwise direction. When you look at the whole diagram itself, AB and BC, actually when you look at the arrows, they are different. So if you consider this, the top here is turning in clockwise direction, then the top here has to turn in anti-clockwise direction. Okay, so you calculate the J, the top you have found by applying principle of superposition. Then you find the J, the polar moment of area, the second moment of area. So you got your JBC. Then strength relationship. Okay, so you have this formula. Then substitute your top, the J, and the radius. Make sure the radius is correct. Is it correct? I think mistake again. Yeah, I put diameter again. Okay, so have a lot of correction to be done. So this is radius. So this is 0.65. Should be 0.065. So you got your shear stress at section AB. Sorry, please refer to this correction here. And then, if I'm not mistaken, this section also the same. Okay, the radius. Please take note of the radius here. It is radius, not diameter. So based on the mistakes that I have made, you should be able to, okay, be careful when you are doing solving your problems. Okay, mistake has been done by me, so you have to correct it. Okay, so the top, the polar moment of inertia, yes, polar moment of inertia or the second moment of area, yes, you use diameter. This you have to use the maximum radius. So 0.18 is wrong also. It should be 0.09. Please do the changes for me. And sorry. And then the shear stress is 11.87 for my case. Okay, yours should be different. Okay, so those are the shear stress in both sections. Remember, change the radius for both. Okay, thanks a lot. And then this is the end of the section on torsion. Thanks a lot. See you.